C3, the imaginary number I. The imaginary number I is equal to the square root of -1. Now, to get an understanding of this, I'm going to draw a circle. And this circle has a radius of 1. Now, this axis that's vertical is going to be called the imaginary axis, IM. And this axis here is going to be called the real axis, RE. Now, we can list any point, for example, point on the circle with an X and a Y. But now, the actual value of that point is given by a complex number, Z, equal to X plus IY. You stick an I in front of the Y. So if you label this, you would say you went up 1, and then you would go up 2 and 3, and here 1 would be here, 2 and 3. But when you write it out like this with the Z, you need to put the I in front of the Y. So like this point right here, though it has a Y coordinate of 1, the point itself would be I, because when you write it as a Z for the point, your X would be 0 and your Y would be 1. So the point would be I. So I can label this point here as 1, since here, this is X and this is Y, here like that. Here, X is 1 and Y is 0. So that would be Z equal to 1. Down here would be a negative I, and over here would be a negative 1. So though this point has 2 coordinates, you can look at this point as having coordinates -1 and 0. -1 on the x-axis, 0 along the y. The point itself is simply -1, because when you write it as Z, the x is a -1 and the y is a 0, so the Z here is -1. So all these points I have labeled are actual complex number in general, where here you use this formula. And since in 2 of these cases y is 0, you wind up with 2 real numbers. But you can consider it as a subset of the entire plane is the complex plane. That's what we like to refer to that plane. So here I'm going to drop down a perpendicular and put an angle in here like this, theta. And then we will find this useful in deriving a very, very important formula. Okay, so just to emphasize, with coordinates, this point here would be equal to 0 and a -1, since the y is a -1, but the point itself would have the -I. And then here, we could say this is 1 and 0 when we give it in terms of x and y. So the x and y are the regular Cartesian coordinates. It's just that when you write the complex number down that point describes, you need to put the I in front of the y. So let's look at this again here, another circle. And put in the axis here, the vertical and the horizontal. And go ahead and put in an angle, theta, here like this. And then if I drop down this line here and have this x, this would be x, this distance. And this distance here would be y. Right? So that distance there is y. However, the point here would represent a complex number, z, which is equal to x plus I, y, where you put the I in front of the y. Now I would like to give another number and go ahead and label this here the imaginary axis and the real axis. I want to put in another line here. Now, just to emphasize, that's one length. I'm going to go here with a perpendicular, a right angle. And to make this a right angle, if I move up here, angle theta, and this is an angle theta, I would have a right angle. Just imagine this right angle here, and then we're just going to rotate like that. So when we do that, we have a right angle between the red and the blue line, and I'm going to go ahead and call this angle phi. So if you add phi to theta, you can see that's going to be 90. But since I have a theta up here, if I take that phi and add it to theta, that's also a 90. Not quite drawn to scale, but if we rotate this up like this, then this distance here, which is y, is this distance here. This would be y also. So these two triangles are similar. Here's the 90-degree angle, and there's the theta. And here's a 90-degree angle, and there's a theta. So this angle here would be your phi. Remember your alternate interior angles. So here, this similar triangle, if you take the theta and go opposite, you have the y. So if you take the theta and go opposite, this has to be equal to that same length y. Then if you go here, the adjacent, this would be the adjacent side, then that would be the adjacent side here. That would be equal to x. So we have x here and we have y. So that means this point here, the complex number for this point here will be minus y plus ix. So you have ix get you here, and then minus y, distance in that direction. Now watch this trick here. I'm going to look at this z. I'm going to call this z prime, so as not to confuse with this z, since I already called that z, x plus iy, then this is another complex number. So if I take I and multiply by z, here's my z, I would get ix, and then I would have plus I squared y. But see, I squared is negative 1, so iz is going to be equal to z prime. This one over here has a minus y and a plus ix. And this is the secret in understanding the complex number. This is the secret in understanding what I is. I remember in high school, what is I, man? Square root of minus 1. And that's because we have this real axis and we can't fit it there. I won't fit along that axis. It's in another dimension. But see, this gives us the secret as to what I does. By multiplying by I, this point becomes this point. And that's a rotation of 90 degrees. So it basically rotates a complex number by 90 degrees in a counterclockwise direction. And that's the secret. See, for example, if you have 1 here and multiply by I, you rotate by 90 degrees in a counterclockwise direction and wind up here at 12 o'clock. Say 3 o'clock and then 12 o'clock. You multiply by I again, we're going to rotate 90 degrees. And that's what I squared is. I squared is -1. If you multiply by I again, you get -I, which is here. And if you multiply by I again, you go up 90 degrees, you get back to 1. And I remember some SAT questions back in the old days here, where you might get a question like, what is I to the 101 power? You go, man, what's that? Well, here the secret is, every time you multiply by I, you go 90 degrees. So if you go I by 4, 4 times, then you go back to where you are. So if you take I to the 100th power, since 4 goes into 125 times, you just simply go around a circle 25 times and wind up at 1. And then if you have 101 as the exponent, 101 i's multiplied by each other, then you simply have one more, and one more, I times 1 is I. So this one here would be I. So you can do this question that looks intimidating. You can do it in 5 seconds, all right, by using this trick. You just simply notice that whenever you can divide by 4, like I to the 16th power, you divide by 4, it's going to be 1. I to the 32nd power, 4 goes into 32, 8 times, you get 1. And then if you have something left over, then you can figure that out by hand. So if you have 33, then you would have 32 would get you here, 33 would get you there, see? And then 34, 35, and then 36, once again, divided by 4 is 9 times, so that works. And then 37, 38, 39, 40, divided by 4 goes into 40, 10 times. So that's a neat trick to remember. So now this is a setup for you to understand a very, very important formula. Now I'm going to label these like I do in the book. This first part here, I'm going to label A, and we'll call A the complex plane. Don't have to place to write it there, so I'll write it over here. The complex plane. This introduces the complex plane. All right, that's like A dot. And then here, B is going to be, for this section, is Euler's formula. Euler's formula. And I'm set up to show you this by this diagram here. So we can write Z as equal to X plus I, Y. But what is X? Cosine of theta. 1 times the cosine of theta. So this is the cosine of theta. And then what is I, Y? What is Y? Y is the sine of theta. Cosine of theta, sine theta. So this is plus I times the sine of theta. Now watch this trick. By taking the derivative of Z with respect to theta, we're going to get the derivative of the cosine with respect to theta is going to be minus sine of theta. And then here, we're going to get the derivative of the sine of theta is the cosine of theta, and the I hangs around. And this is Z prime. Let's look at Z prime here a little more carefully. Z prime is minus Y, which is minus the sine of theta, plus I times X. Well, X is the cosine of theta. So by multiplying by I got Z prime, multiplying Z by I got Z prime. But if I also take the derivative of z with respect to theta, I get the same thing. So that means I can write this. So this is z prime. But I'm going to notice that here, if you take I times z, you're going to get I times the cosine of theta minus the sine of theta. So we're going to get this two ways. We can multiply by I and get there, but we can also take the derivative and get there. So this has to be Iz. The derivative of z with respect to theta is Iz. These are the same expressions. But now comes the magic. Because what is the function z if you take a derivative and get the same thing back with an I in front? The answer would be e to the I theta plus some constant. Where the only thing we need to do here now is we need to find out that constant. And we do that by putting in 0 for theta. So in other words, when theta is equal to 0, then the cosine of 0 is 1. So you have to get 1. So that means z is going to be 1, and that implies that the constant is equal to 0. So we have z is e to the I theta. Now, just to review for you here, taking the derivative using the chain rule, when I take a derivative, dz, d theta, I would say I'm going to get the same thing back times the derivative of what's up in here. Now, let's do it with all the steps, all right? What you would do is let u equal I theta, so that you would have e to the u power. And then remember the chain rule that if you have, say, dz, d theta, you would first do a dz, du, and then do du d theta. That's a chain rule that we have introduced earlier. So dz du, the derivative of an exponent like this, say e to the u, take the derivative with respect to u, is simply the same thing. That's e to the u. And then du d theta, that would be what's in front here. You would get then times I. So that is I e to the u, and then you would put in for the u I theta, and you would then get this result. So I'd like to show that in detail there for this time because we're reviewing things here. So that relationship that we have here is very, very important, and this is Euler's formula. When you write this, z is equal to I theta, what we basically do is write e to the I theta, and then we write down that it's the cosine of theta plus I sine of theta, because that is the z, that's the same thing. So the identity is this part right here. Very, very important in physics, and Feynman in his lectures like at Caltech would refer to this as our joule. Our joule. Very nice. Let's go here to look at Euler's identity. This is referred to as Euler's formula. Euler's identity is a magical equation that relates 5 very, very important numbers in mathematics. 0, 1, I, pi, and e. So the secret here is to put in pi for theta. So e to the I pi is equal to the cosine of pi plus I times the sine of pi. Now, the sine of pi is 0, and the cosine of pi is -1. So therefore, this result gives us e to the I pi equals minus 1. But now what we would like to do is add 1 to both sides of the equation and get e to the I pi plus 1 equals 0. And this is the magical equation. We have an equation that relates 0, 1, I, pi, and e where they appear once and only once. What a mystery here. How is pi, I, and e related? Well, this shows you how they're related, and the secret is in this circle that brings this together. Brings your angle in there, you have your imaginary number I, and the fact that you can take a derivative of something and get the same thing back, almost the same thing back, brings in the e. Because remember, when you take, say, dx of e to the x, you just have that, you would have e to the x. So here we're having the derivative of something, bringing the same thing back, something almost the same thing back, and that's how it all fits together. I like to call this our opal. I like to call that our opal. And this brings me to remembering the time where we made gingerbread houses in a competition in Rhodes Robinson Hall, the science and mathematics building complex. Our gingerbread house, we won with our gingerbread house. And look what we put on the roof. We have E equals mc squared and Euler's identity. Now part D, I want to show you how to write the cosine and the sine in terms of exponentials. So here, e to the I theta, we have here is cosine of theta plus I sine of theta. Now, e to the minus I theta, if you put in a minus sign for the theta, the cosine is the same because cosine is an even function, so this is still the cosine of theta. But since the sine is an odd function, this becomes a minus sign. So now what we're going to do with these two equations, we're going to add them up. If we add them up, we get e to the I theta plus e to the minus I theta. These cancel, the I sine theta, and you get that's equal to 2 cosine of theta. So that means that the cosine of theta is equal to e to the I theta plus e to the minus I theta, all divided by 2. Now, instead of adding these equations like we did here, A, D, D for add, we're going to subtract. We're going to subtract. So then, e to the I theta minus e to the minus I theta, like this. Now the cosines go away, and the minus sign here makes that positive, and you get 2i sine of theta. So that means the sine of theta is e to the I theta minus e to the minus I theta, all divided by 2i. Beautiful result. And very important in physics and engineering.